A particle p travels along a straight line between two fixed points, A and B, and its velocity changes with time as shown. Moving to the right counts as positive. Here is what we are given. The velocity of p measured from the moment it passes a heading towards B. And 4 things to find. Which side it is on, the acceleration at 1.3 seconds, whether p reaches B, and with a second particle q when both move left. So here is what we are working with. The velocity of each particle, the rule that right is positive, and that A and B are 15 meters apart. From these, we answer all 4 parts. Let us picture the motion on the straight line. We mark the start at A. Right is the positive direction. Here is particle P sitting at A. The key idea is direction. A positive velocity means it moves right. A negative one means it moves left. We also use 2 tools. Differentiate the velocity to get acceleration, integrate it to get displacement. And the particle is furthest along exactly when it stops, where the velocity is 0. Part A. Which way does P move the instant it leaves A? This is the velocity of P. We park it on the right since every part uses it. At the time is 0, so we put 0 in for t. The velocity comes out negative. A negative velocity means it heads left, towards B, so B is to the left of A. Therefore A sits to the right of B. Watch the common slip. The negative sign does not put A on the left. It just means P heads towards B, which is on the left, so A is on the right. Part B. The acceleration at 1.3 seconds. Acceleration is the rate of change of velocity, so we differentiate using the power rule. Differentiating term by term gives 6t plus 4. Now put 1.3 in for t. That is 11.8 meters per second squared. Part C. To see how far p travels, we need its displacement. Displacement is the integral of velocity, so we integrate using the power rule. Integrating gives t cubed plus 2t squared minus 15t, plus a constant. We measure from A, so at the start it is 0, which makes the constant 0. So the displacement of P is t cubed plus 2t squared minus 15t. P moves towards B, slows and stops for an instant. That is as far as it gets. It is furthest along when the velocity is 0, so we solve that. Set the velocity to 0. This factorizes neatly. Time cannot be negative, so we keep 5/3 of a second. Watch P glide left, slow, and stop just short of B, then turn back. Put that time into the displacement. Working through the fractions, the furthest displacement is minus 400 over 27, about 14.81 meters. 14.81 is short of 15, so P does not reach B. For the last part, go back to the start and ask when each particle moves left. Part D. P moves left wherever its velocity is negative. Moving left simply means the velocity is below 0. Using the same factors, we need this product below 0. A product is negative only between its two roots, so t is between -3 and 5/3. Time starts at 0, so p moves left from 0 up to 5/3. Now particle q the same way. Add q's velocity to our list. Q moves left where its velocity is negative. That factorizes 2. Between its roots again, so Q moves left between 3/2 and 2. Both move left only where the two time ranges overlap. On a timeline, P moves left across this amber stretch from 0 to 5/3. Q moves left across this stretch from 3/2 to 2. The overlap, where both move left, is this narrow mint band. So both particles move left only between 3/2 and 5/3 of a second. To recap, A is to the right of B since the velocity at A is negative. The acceleration is 11.8. P does not reach B. It gets about 14.8 meters, short of 15. And both particles move left only between 3/2 and 5/3 of a second.